today we'll see about the bilinear surface. So before we go into any type of surface representations, we should let's see about the introduction or some of the basic basics of for a surface. So a bilinear surface that we take is nothing but, so the moment we consider a surface, it is having two dimensions, and then where it doesn't have the third dimension. That is where we can say that it has got in x, y, and directions, x and y directions, but not in the z direction. There's no thickness for it. Now, for any kind of surface, we can represent it in the mathematical form to find any of the points that is present onto the surface. So let us consider a bilinear surface over here, where what is being indicated in the diagram is that from the moment we say it is a surface, it is need not always have to be a flat one. Okay, it can be a curved one also. So the major thing, if it is a flat one, it's easy to calculate and represent things in different ways. But the moment it is going to be in a curved form, then it is going to be a little bit complicated. So we need to make use of mathematical equations to represent each of these points, as they're going to vary in both x and y directions. Right. Okay. So first thing is that for a surface we need 4 points. So let us call these 4 points, 4 corners of the surface as P00, P10, and P01, and finally P11. So it's nothing but if we take up a surface, okay, and say for example, if this is x direction and this is the y direction. Okay, so we'll just call this as 0, 0, and this is going to be in x direction. So let us assume unity distance, okay, 0, 1, and this is going to be in y direction. So 1, 0, and this is going to be 1, 1, right? So this is how we used to represent with respect to x and y coordinates. The same thing has been made use over here, and the corner points, the corners are represented by P. Right, so this is going to be, instead of x and y direction, we are going to take over here as u and v. Yeah, u and v. Okay, right. So this is going to be P00, P10, and here in the y direction P01, and finally P1. So the moment that we are going to move, say for example, in the v direction. Okay, and so this line is going to be made up of several points, and it's going to have a value in the v coordinate. So anywhere on this line, if you want to know the point, okay, then we can just call it as of now, for p of 0, v, right? Because it's in the v direction. The moment that we go in for the u direction, then we can go in for p of here they have represented as 4, just they have taken one of the interpolation points. So in general, we can write it as P of u, 0, right? U, 0. Yes. So similarly, when it comes over here, any of the points over here, again in the v direction, okay, then it's at the end of the unit distance. So P of 1, 0 is the corner. So when we start moving in this particular direction, anywhere on this line, it's going to be P of 1, v, where the value of P at the in the v direction. And here also similarly, it's going to be P of u, 1, because it's on to the fourth sector. So now the corner points distinguished by P of 0, 0, P01, P10, and P11. Yeah. Now with this, now to have these boundary curves, straight lines, they can, that is especially the top and the bottom one, we can write this equation. So we are now considering only this particular line, p of p of u comma 0 and p of u comma 1, right? So if we want to trace any point onto this, first of all, let's write the equation for this. Okay, so p of u comma 0 for this particular line can be written as p of where any of these points onto this line is going to lie on between p of 1 comma 0 and p of 0 0. So it's going to be in between this. So thereby we're going to have p of 1 0 minus p 0 0. Okay, into, it's in the u direction, right? It's in the u direction, so we are going to make use of the multiplied by the u coordinate, right? So where it is, how far it is going to be there, right? And plus p 0 0, the measure, right? So when we rewrite this particular equation, okay, we can write it as p of 0 0 into 1 minus u plus plus u into p of 1 0. So similarly, when we take consideration, start measuring from the other direction, that is from here, right? So p of u comma 0, sorry, p of u comma 1. So this equation can be written as, that is for this particular line. Okay, so in between this, p of 1 1 minus p of 10 multiplied by u, okay, plus p of 0 1, right? Okay, right. So this can be now written as, that is for the, sorry, the top line. Okay, the mistake. Yeah, this for the top line. So for the top line, it's going to be of p of 1 1 minus p of 0 1 into, it's going to be in the u direction, right? So into u plus p 0 1. So rewrite this as p of 0 1 into 1 minus u plus u into p1. Now, by defining these four boundary equations, especially the boundary curves, right? Anywhere inside this, any point inside this surface, inside this boundary, we can find it by interpolation functions, where we make use of the parameter u, okay, where we'll generally consider, however big the surface or the smaller it is, we generally consider it from whose value is going to be, for the parameter value is going to vary from 0 to 1, that is from 0% to 100%. We can take it in simpler terms, right? Okay, so now with this resulting the equation, okay, this is going to be in the form of, when we take any point over here inside the surface, right? So it's going to have a u coordinate, right, and a v coordinate. So ultimately this is going to be p of u comma v, right? So for this we have to write the generalized equation. So for that, p of u comma v is equal to p of u comma 0 into 1 minus v plus v into p of u comma 1. So now, once the moment that we are going to make use of this p of u comma 0, right, that is there in the u direction, plus if we have a point anywhere over here, then we have to go on for this one also. So first we are going to take it up only for the u direction. So that is why p of u comma 0 is there, right? So p of u comma 0 into 1 minus v. It's going to be, say for example, it's going to be at a distance of, if this point is there, then when we take this, next for this one, it's going to be 1 minus this v. So this is 1 in the v direction. The entire length is 1 unit. So minus v, so that we get that particular point from measuring from 0. Right. So plus v into p of u comma 1. So p of u comma 0 we already know from here, right? Okay, so 1 minus p into, they rewrite this equation, they get this equation, simplified equation over here, right? So that's 1 minus u of p naught p00 plus u into p10. And similarly, we have the next thing is, it is v into p of u comma 1. So u comma 1, the equation, that is this one, will be taken up over here. Right, which is 1 minus u into p01 plus u into p11, and it's already multiplied by b. And now when we simplify this, open the brackets and simplify this. Okay, so we are going to get an equation like this, where it's going to be 1 minus v into 1 minus u p00 plus 1 minus v u into p10 plus v into 1 minus u p01 plus v into, sorry, uv into p11. Now putting this equation, so this is the equation for after opening the brackets for any point inside the surface, I mean on the surface, that is within the four boundaries. Now that can be represented in a matrix form, right? So 1 minus u and the other value is u, close the bracket, and then we have p00, p01, p10 and p11, and then another matrix of 1 minus v into 1 minus v, and the next one is v. So wherever this u is going to be between 0 and 1, and even the values of v is also going to be between 0 and 1. That's from 0 to 100% we can assume, right? Okay, so this is the generalized equation for the bilinear surface, where we can find any point on to the which is present on the surface within the boundary by using interpolation. So next we'll go to yes. So let's see the bilinear equation surface. So here the other data that is present. Okay. Right. So the first thing over here. So bilinear surface, it's going to be, we are going to derive the interpolating by interpolating the four data points. So we need to have, so for any surface, we need to have a closed surface, enclosed figure. So this is the reason why whenever when we do modeling, and if there is modeling and even in design also, without any shape that is not enclosed, it cannot take any kind of calculation. If it is open in a small place, it is not possible, because one of the data is not going to be there. The fourth point is not going to be there. So the 4 points are important. So by making use of parametric equations, yes, they have used the same terminologies here also, right? P00, P10, and P01 and P11. That is the 4 corner points or the boundary points for the surface. Okay. Right. And yes, now yes, they have taken up the now if they have to derive an expression, as I just mentioned, in u and v directions. Okay, so what they're going to do is that they're going to divide the line segment. Okay, that's in the x and that's in the u direction and y direction. So that first they're going to resolve it only in the u direction and then into the v direction and to find the any point on the u directional line or v directional line. So that once we get the equations for this, then we can go for any other point between the u and v axis, right? So the same equation is being written over here. Yeah. And Okay. So here, the u and v for any point on the surface will traverse and the entire surface consistently with increment of the parametric values of u and v from 0 to 1. That's the basic assumption that is going to be there. So here they have given a little bit different diagram. So the same thing. So this is the first corner P00, this is the second corner P10, third corner P01, fourth corner P11. So this is the u direction and this is the v direction, which they have indicated here. So anywhere over here on the midpoint, they have just taken it up so that it's u p of u comma p of 0 comma 1, and this is going to be p of 0 comma 1, right? So this is going to be to v distance, and this is going to be 1 minus v distance. So similarly over here also, when you go in the u axis, so this is going to be up to, this is going to be p of u comma 0, right? Because this distance is going to be u, and this distance is going to be 1 minus u. Yeah, it's going to be 1 minus u. So that is what has been indicated over here for a distance of u, and this is going to be 1 minus u. So this point that is there at the center that we want to know on any arbitrary point or inside on the surface within the four boundaries, represented by p of u comma v, where it has to travel in u direction as well as in v direction. Now, yes. So the moment that they substitute over here, the same thing can be the same equation has been obtained over here by, first they resolve it for p of u comma 0 and p of 1 comma v, and then get it over here to find value of p of u comma v. So then once they are going to substitute these for a point lying in both u and y directions, yes, we are going to get the same equation over here and written it in a different matrix form, right? So where we have p of 1 minus u over here, right, which is going to be p into multiplied by p00, put it up into the next matrix. So u into 1 minus v over here, right, and then you're going to get on multiplication, they're going to get, once they open the brackets, you're going to get 1 minus u into v and uv, right? So consistently, those particular corner points have to be put up in the other matrix where u value and v value will lie between 0 and right. Okay. So the next thing is that once these equations are being always done, we have to verify that these points as imagined to derive the mathematical equations should lie onto the surface. The four data points are onto the corners of the surface of V, right? And then, so yes, so this is obtained by simple blending of corner points by weighted method, nothing but the interpolation. Okay, and so these things are very much the basis for representing the surfaces on any type of for used for any type of mathematical. I mean the 2D surface representations where we make use of Bezier surface or Hermite surface, like or B-spline surfaces. So this is going to be the basis for all of these surface studies. Okay. Right. Okay, yes. Yes, so coming to this Bezier surface, okay. So nothing but it is going to make use of the we are going to make use of the Bezier curves. Really, the first important thing, okay. So here, what is this? Is that the first thing is that over here in a Bezier surface, before we go in a Bezier curve, what we have taken is that we have taken only we have taken 4 corner points, that is the control points for the Bezier curve that is to be drawn. Now, when we group these curves in U directions and Y direction, sorry, in V directions, we are able to get a two-dimensional uh, figure, which is nothing but a surface, which will have a curved shape. So, having a series of set of control points for each of these curves. Right. So the figure that represents over here is nothing but, now if let us consider that this is the first curve extending in U direction. So P00, P10, P20 and P30, right? It's going to be extending only in the U direction, okay, but not in the V direction. Now the next one we'll go is that we'll have one more curve, Bezier curve, having another set of 4 control points just like this, okay, which is curve number 2, right, offset at a distance, okay, by 1 unit, let us assume, okay, right. So we'll have for the second curve P of 0, 1, and this curve extends only in the U direction. So we'll have the next control point P11, then P21 and P31, okay. So yes. Okay. So this is offset by 1 unit in the V direction. So the third curve is going to be Bezier curve is going to have P02, P12, P22, and P32. Right. This is the third curve extending in the U direction, offset by 2 units, okay, in the V direction. And finally, another curve of P03, P13, P23, and P33. Right, in the 4th direction, which is offset by a distance of 3 units, right? It is offset by a distance of 3 units. So now we have, as of now, we have 4 curves like this, 4 Bezier curves like this. Now, similarly, we can have it in the parallel direction also like this, right? So now when we take this, we are going to have a complete surface with interpolation points. So we have to have the first curve in V extending only in V direction, P00, P01, P02, P03, right? And now draw a parallel Bezier curve extending in the U direction by a unit of 1, okay, but the curve is going to travel in the V direction, offset it in the U direction, right? So P10, P11, P12, P13, and so on, right? So ultimately, when we draw this, okay, we are going to have a control over these, not only the 4 corners of the surface that we want, okay, not only the 4 corners, but also at the intermediate points. I mean, to frame the surface, right? To frame the surface. The closer these are, the more the smoother the surface is going to look like. Yeah, this is important. So when we take into consideration for each one of these things, okay, it's nothing but a group of curves that has been joined together in U directions and V directions, and each one of them have their own set of control points, right? Each one of them have got their own set of control points. So, and why do they need this is that we can manipulate the surface uh, uh, the shape that is going to be formed, and we can control them, right? And the most important point in all these things, all of the CAD models will be made such that the equations are of the third order degree polynomials only, right? Nothing more than that. We do have in mathematical equations where the equations can be of higher order elements, of fourth order, fifth order, and so on. But when it comes to for computational thing, we cannot have one curve with third order degree and the other one with fourth order degree. So there's too much of complication with respect to solving, as well as to join these two curves having different degree of orders, right? So thereby uh, all the curves, whether we make use of Bezier curve or Hermite's curve or NURBS or splines, okay, all of them will have only the third order degree, right? So that the joining is going to be easier. Right. So that is why if we take a look at this, for all of these things, only 4 control points will be used always, so that the degree of equation will be for the third order degree. Any kind of software that is being used also is going to make use of this degree. Right. So the next thing is that at the moment that we have third order degree, as we had seen in the previous class, say for example, we have one set of Bezier curve like this, and we have another set. So it's going to be this 1, 2, 3, 4, the second set. Okay, then what is going to happen is that to join these things, okay, now it has to form, if we have the 4 control points here, then the Bezier curve is going to be like this. So we have 1, 2, 3, 4, 5, and 6. So if we take our now 6 control points for the curve, and we are going to manipulate this, then it's going to be a really difficult task, because it's going to be the equation has to be solved for the fifth order of degree. And instead of that, what is going to be done is that it is going to be divided into 2, so that we have one set of control points, that is 1, 2, 3, 4, and the other set of control points is 3, 4, and 5. Okay, so that with 4 control points in each set, the degree of polynomial is going to be only for 3, right? So thereby, what is going to happen is it is going to be curve number 1 and curve number 2, where it has to be merged in this common area, right? So during these things, when you are going to create a curve or even surfaces, this is very much important, right? Both these curves are of the third order degree polynomial only, so joining them will be easier, computation will be easier, and the moment we look at it, the joining place will not be seen at all. We cannot differentiate it at all, right? It will be a smooth surface, right? Okay, right? Okay, right. So this is the reason why we are going to make use of third order degree polynomial, so that the joining is going to be easier. The tangents join at these points is also going to be a smooth surface or a line that will be obtained. Right. So the moment that we are going to take this, it is going to be curve number 1 and curve number 2, and joining this will be easier. And at the same time, we can move these control points to change the shape of the curve also. Right? So this is the reason why it has been kept with third order degree, first thing. And then comes the most important thing, is about the patching of surfaces. Okay, especially that we will do in meshing and even in the surface modeling also. So when we design, when we model the surface, generative surfaces for any CAD model for an automobile part or for aerospace components, right? So we are going to do it in smaller segments and join it by smooth curves, right? Okay, and if it is a three-dimensional one, it's going to be patching of the three-dimensional surfaces. Sorry, the two-dimensional surfaces in 3D environment. So we extend as just mentioned, we are going to extend the concept of Bezier curve only, Bezier polynomial for Bezier surfaces. Okay, where it's one more higher dimensional, that is, it's going to have one more curve in the second axis also, or the v axis also. So when we go for this, it's going to have any point within the surface is going to p of u or p of u comma v. Okay, so which is going to make use of two Bezier curves, one in the u direction and the other in the v direction, right? So the parametric values of u and v will lie within 0, 0 and 1. So let us just see back with the Bezier curve first. And so this is the Bezier curve that we had. Yeah. Okay. So the Bezier curve equation is going to be, if we take it up in u direction, p of u is going to be equal to sigma I equal to 0 to n, okay, into n in I to n, u to the power of I into 1 minus u to the power of n minus I into pi. So any point onto the curve. So any point onto the curve, yeah, right, is what is our p of u, where the curve is going to be extended in the u direction. Right? This is our Bezier equation. Similarly, we need one more term in the v direction. So that is nothing but p of v, right? So p of v, we have to change these terms. We can take it as j and m. So j equal to 0 to m, and here we will have j and m over here. Okay, so u to the power of j 1 minus, sorry, v to the power of j into 1 minus v to the power of m minus j, p of j, right? That is the initial to final values that we can take it up. Right. Okay, so just again. Yes. So now if you look at this, p of u comma v, so as I said, if we take up only in u direction, sigma I to 0, I equal to 0 to n, okay, right? And we are going to have then in the b direction, sigma j equal to 0 to m, p of I comma j, because just going to be in the I and j, we have one value of p of I and p of I, and whose parametric values lie between I to n in the u direction, and the other one lies between j to m in the v direction, where the u and v values are going to be within 0 to 1. All right. So we are just going to merge these two equations of a Bezier curve extended in u direction and in v direction. So stop here for today. Yeah.